All right, so for today, we're going to tackle two things. I'm going to quickly talk about the next phase of our group projects, which is the database phase of our project, which is actually kind of separate from the visualization, but we're kind of working through both the visualization side of things and the mechanical side of things in this class, both for group projects. So we'll talk about this. And then we're going to start our discussion of database manipulation language today. So we'll do a quick lecture. So our first database project is due in a couple of weeks. And the idea here is that I'm going to give you a fictitious company, and I'm going to ask you as a group to model how this company would use a database to manage their various data sources. So the fictitious company, which I didn't make up, I'm borrowing from Dr. Becker, is Wildcat Pizza. The idea is that this is a walk-in restaurant that's located here in College Station, Texas, and customers have to use hand signals and yells to place their orders. Only in College Station, Texas could this actually be a viable idea. I think all of us can agree that they could pull this off, and the students would probably dig this. They offer a limited menu, so we're going to keep that side of the database fairly small. And after customers place their order, the employee, which are fish, are going to handle the orders. They record everything on a cook sheet, and then they confirm things, and they record obviously a bunch of information for the back end of the restaurant. And then we're going to go ahead and process that order and make sure that we are figuring out what customers are providing to us, what the amount that's due, all that kind of stuff, what they have to pay for, getting the cash, all that kind of stuff. You can imagine how this restaurant's working. So I think this tells a fairly good narrative. Fish aren't allowed the privilege of touching the pizza, so the completed cook sheets are going to send to a yell leader, who's a cook. They prepare the pizza, and then the leader provides if the order's ready, and the customer gets to come pick up their pizza. So again, just read through the narrative. It's fairly straightforward. But what we want to do as groups is then come up with a database that would capture all of the relevant information. So I want you to keep the narrative in mind. I want you as groups to determine what is the critical information that we actually need to store in the database versus superfluous information that obviously is happening at the restaurant, but not necessarily something that would need to be stored in a computerized fashion. So you're gonna have to figure that out. And then how do you model it? And that means the best way to store entities and their various relationships, so the data is stored in a normalized fashion, in an efficient way, and also stored in a way that enforces the real business rules. So everything that's supposed to be happening in the business, the database supports, and the database is constrained, so you can't do the wrong thing inside the system that isn't actually what's being reflected in the real world. And so there's some additional information there about referring customers and discounts and all kinds of stuff. What I'm asking you guys to deliver for this first phase is a conceptual model of the database for Wildcat. So use all of your enhanced entity relationship diagram techniques to come up with your documentation. It should include everything. This should be an extremely thorough diagram. So all the entities, all the attributes for the entities, all of the relationships between those entities, and all of the max and min cardinalities. If you are making any assumptions, you should also document them. So don't make any assumptions that are contradictory to the narrative. Don't make something up. But if there's something that seems to be missing from the narrative or ambiguous, and you as a group interpret something in a particular way, make sure you write that down so we know what your assumptions are moving forward. So conceptual data model, that's the lion's share of this assignment. The next part would be the logical data model. So make sure that something follows third normal form and a relational schema notation. Make sure that you include any referential integrity arrows in terms of how things are being informed, and make sure that it's consistent with your conceptual model. Now, of course, that might mean that you're adding some additional integrity and you're restructuring things a little bit, but we tend to have conceptual data models and logical data models that are very similar to one another, just a slightly different notation. So they should be pretty close. And then last part is a design repository. So I want you to think about the specific metadata that's going into your database design. So what kind of information is going in? And that basically is it text? Is it numeric? Is it date? What kinds of specific pieces of information would you store for each of the attributes and each of the different entities or tables in your database? And this is due, like I said, in a little over a week. It's due in 2 Thursdays. Any questions on what to expect for this first SQL project, this phase 1 of the database project? Does it make sense? Yeah? Okay. Well, let's jump into our lecture for today. We're going to talk a little bit about the data definition language, which is DDL. Again, my screen shared here. There we go. So let's talk a little bit about how databases work. Resume slideshow. Is everybody seeing my slideshow now? Okay. All right. So data definition language is how we're actually going to get things transitioned from our diagrams to an actual SQL database. We're going to talk about SQL Server, which is the database management system that we're going to be using in this class on Thursday. You will note on eCampus in your gradebook, you will now see 2 new columns. One is your username and one is your password, and those are for the SQL Server that we're going to be using on campus. I'm going to post some instructions for SQL Server that you can follow to get ready to work through the stuff we're going to be talking about together on Thursday. And one of the things you're responsible for doing between now and Thursday is actually getting SQL Server installed. It works natively in PC. It does work in a Mac environment. You have to install an additional Docker application that it runs inside of, but it is doable. I'm not providing technical support on this side of things. I know that you guys can figure out how to install the software. It's not particularly difficult, but I will provide just some rudimentary instructions on where you can find the software and get it installed. That'll probably happen sometime later today. And I'm going to encourage everyone to have that installed by Thursday. If you don't have it installed on Thursday, you can certainly follow along with what I'm demonstrating, but you won't be able to actually do it yourself. And so you'll want to get that installed as soon as you possibly can, if not by Thursday. So one of the things that we're trying to do with database management is, after we've gotten all of our data structured, can we ask questions of that data? And the means of doing so in most databases is something like SQL, which is an abbreviation for Structured Query Language. You've probably heard the term SQL for most of your lives, but some of you have probably never used it, or if you've used it, you've used it sparingly. It is a common language across a variety of different software packages for asking questions of data. The syntax does differ a little bit from specific software platform to software platform. So we're going to be using SQL Server, which has a fairly standardized version of SQL, but there are some things that are specific to SQL Server that you can't do in MySQL. And there are some SQL Server commands in MySQL that you wouldn't be able to use in Oracle. So there are some syntax differences, but most of what we're going to be talking about as far as SQL in this class is generic structured query language that works in almost any environment. So a lot of what you're going to be learning in this class is going to be transitionable to really any platform that you might use for database. I talk about databases. We're going to be using a relational database management system. Again, the one we're using is SQL Server. Some of the competitors would be something like Oracle or MySQL, which is an open source. I've used MySQL before. In fact, this class was based on MySQL in the past, but we have a version of SQL Server freely available to us in Maze, and so that's going to be the platform that we use for this class. I am agnostic. I don't care about the platform. That doesn't really matter too much to me. We're just picking one that is a resource that's available to us here in Maze. So a relational database management system is software that helps us with a collection of tables, how those tables relate to one another, what are some of the common values between those tables, and then how can we get knowledge and information out of the data that is stored in all of those tables. That's the primary function of a database, is storing information in the most efficient way possible and then getting information back out of that database whenever we need it. And that's what we're going to be doing for the next couple of weeks in this class. There are a couple different terms we're going to see when we talk about our SQL environment. We tend not to get too deep into catalogs and schemas, which kind of talk about the general overview of the database itself. We're going to start our discussion with data definition language, because this allows us to set up a database to start with. This is not a tool that you typically use for manipulating the data. That's going to be data manipulation language, the next one we talk about. So this is going to be something you use to get it set up to start with, and then you get your database populated, and then the remainder of the time that database exists, you're going to be using database manipulation language, or perhaps the control language, to make sure everything is functioning the way that it's supposed to, and that you can get value out of that database. So we're going to start with a tool that is used kind of infrequently, because we don't make new databases all that often. We need to, obviously, for this class, create our databases from scratch, but once those databases are authored, and we give the right people authorship of those databases or access to those databases, they would be using DML or DCL to actually do the manipulation of the data itself. So we're doing some authorship to start with, and then later we'll talk about how we would manipulate the databases that we've created. So data definition language, the biggest step, most important step, is going to be our create statements. This is how we're going to create portions of the database that belong to a particular user, create the tables that exist inside that database, and potentially create what we call views. Views are a specific narrowing or broadening of how we see information in the database. Most of the time when we talk about views, we're going to be talking about narrowing the focus. So we could imagine a table that has all of the student information for students here at Texas A&M. But a view that might be interesting of those students might just be last name, first name, and email address. That's all I care about. So that would be a view that shrinks the view down to just 3 columns of the data. Another view might be, I only want to see freshmen. So I could narrow the number of rows that we see inside that table, and I could shrink it down to only see students that are first-year students here at Texas A&M. So if you think about narrowing what you actually can see inside a larger data set by limiting the number of columns or limiting the number of rows, that would be a view. The other way you could use views is some sort of combination of tables. So if you imagine combining customers and the products that they ordered, some sort of combination of those things, and showing all of that in one big table. That's not how the data is stored. We'd have customers off in one table, we'd have products off in another table, we'd have some sort of associative entity that marries those two together in terms of orders. But maybe we want to see it in one really large table for some particular reason. That would be another use of a view. So we'll talk about creating views where we either broaden or narrow the scope of the data that's being displayed using some sort of data definition language for things that are commonly being viewed. Other kinds of statements we might look at would be creating character sets or collation or translation or assertions or domains. Most of that is outside of the scope of this class. We'll see a little bit perhaps of assertions, but the rest of that for the most part we won't be dealing with in this course. In terms of creating our tables, most important thing is going to be we have to figure out the various data types for our attributes. The most common data types for a database would be numeric of some sort, integer or decimal typically, text, so you can type letters and characters and numbers for a name, a description, some sort of address that includes both numbers and letters, only letters. That would be some sort of text. Could be some sort of time date stamp, might include just the date, might include just the time, might include both. Might be some other data types as well that we see as we move forward. So we're going to want to define what kinds of data types we have for the various attributes, and every attribute has to have a specific data type. We're going to want to try to use the one that is as narrow as possible without breaking the database. So if we can make something integer, that's great. We want to try to keep things as narrow in scope as possible. But if it is possible that a number needs a decimal place, even rarely, we'd want to increase the scope of that data type to decimal. So you don't want to change the data type to be so narrow that it's going to make the database not function correctly. And the best historical example I can think of where somebody made a mistake here was Y2K. And I know this is ancient history for everyone in this class, but way back in 2000, there was a bit of a crisis because many databases had programmed year as a 2-digit number. It could be at most 2 digits. Well, the problem was when we got to 1999, we were storing number 99 as the year. When you typed in 00, the system didn't know if that was 1900 or 2000. And potentially that meant that dates got all kinds of wonky and then math got all kinds of messed up and then the databases could get broken or provide erroneous information and it became a bit of a crisis. So they had to go back in and reprogram to allow for a larger date, 4 numbers instead of 2 numbers, so that that kind of error couldn't occur. And I hope they were forward thinking so that they're ready for the year 10,000, because when 9999 rolls around and we only have 4 digits available for years, we're going to go through another 10K crisis. So hopefully they're ready for that when we get there. After you figure out your data types, you need to identify if a column can or can't be null. Sometimes information is optional, so it can be empty, but sometimes information is required, so you want to identify that. Next, you want to identify what is your primary key and are there any foreign keys that exist as a primary key someplace else. You need to think about that a little bit. It's possible that some data points have default values. So without us overriding it, there could be a default price of 20 bucks, or there could be a default phone number or what have you. So we might think about that a little bit. We might then identify some constraints on columns. There could be specific things that have to be entered in a particular part of a table. That's certainly possible. And then we would create the table and any associated indices. So how do we want to potentially sort a table and then search through that table? So often it's going to be the primary key, but there might be other indices where we're going to be regularly sorting something and searching for something. And so we'll provide an index there to make that more sortable. Best example of this would be human information. We're often going to have a primary key, which is something like your social security number, your UIN, but we're often going to be searching by your last name or your first name. So we might add additional indexes for name that are not corresponding to the primary key. So some common data types, like I said, would be character or text. Often that's abbreviated as string. You might have something that's character that allows for a variable length. You might have something that has a specific fixed length, like the year 2000 had 2 characters. So we can talk about that a little bit. There's something called a binary large object. This allows for really kind of attachments that you could have associated with a specific row in a table. We might have numeric values, and again, typically it's going to be either numeric or integer. So numeric would be allowing for some specific number of decimal places. Integer is just that, whole numbers. We might have some sort of time, date, stamp sort of information. We could also do things like true, false, on, off, yes, no's for our data types. These are some of the most common data types that we might see in SQL. So we have spent a bunch of time already this semester working through these entity relationship diagrams. And I don't think I said it earlier, but I really want to thank the class for doing a great job of making this a collaborative experience so far. We did a whole bunch of examples of these, and as a consequence, you guys did quite well on exam 1, and that credit is due entirely to you folks. All I was really doing is helping you guys have constructive conversations amongst yourselves. A lot of you were presenting this information and we were just going back and forth on it. So I really appreciate that. And I just want to make sure I said thank you if I hadn't done that before. So we spent a bunch of time doing diagrams like this to illustrate our various entities, how we would uniquely identify each entry in these entities. So customer ID for customer, or order ID for orders, or product ID for products, and the various relationships, whether they are mandatory or optional, whether they are one-to-many or one-to-one. Of course, we know we don't allow for any many-to-many relationships. We replace those with associative entities. What we would want to then do is translate this information to something that we could put into a database. So here's how this might work. This is 4 different create statements. This would be programmed into SQL to create 4 different tables. The first table is our customer table, and you can see it's named customer underscore T. And they're creating this table with a variety of different attributes: customer ID, customer name, customer address, city, state, and postal code. You can see the various data types. Customer ID is a number that has 11 digits and no decimal places. Customer name, address, and city are all variable characters with specific lengths. The customer name can be at most 25 characters, customer address 30 characters, customer city 20 characters, customer state 2 characters, and that's exactly 2 characters. And then customer postal code, variable characters with 9 as far as length. So it could be the 5 and 4 digits. And you can see 2 of those fields are not allowed to be null. You must have a customer ID and you must have a customer name. The rest of those attributes, it looks like they could be empty. So maybe the only thing I know about you is your name, and I've entered a customer ID for you. Everything else I may or may not have to start with, and that's acceptable for this database. Finally, in this first create table statement, you see something that says constraint customer underscore PK primary key, and then in parentheses, customer ID. So this is creating a constraint. It's giving it a name, customer underscore PK. That's the name of the constraint. It's saying that this kind of constraint is a primary key constraint. And it's saying that the primary key is the customer ID, which we already created as an attribute for this table, right? So this is the kind of syntax we're expecting for creating our tables. And the order of things matters. You want to create all of the attributes first and then create any constraints that are based upon those attributes. And it does matter various data types as well. And of course, if you're using something like a primary key, that has to be a not null field. Primary keys are required. You have to have an identifier for each table. And every table we create in our databases is going to have a primary key of some sort. You can look through the remaining 3 create tables. The second table, which is the order table, does have a foreign key, and it specifically references the customer ID for an order. This second create statement has to be second because its foreign key has to exist someplace else ahead of time. I can't create the order table unless the customer table already exists, because I can't create the constraint of the order underscore FK foreign key, which is referring to the customer ID in the customer table, until the customer ID in the customer table exists. So it wouldn't work if the customer table wasn't already created. Doesn't mean the data is necessarily populated. You may not have put anything in these tables, but the structure is there. And so you can't create the structure for the order table until the customer table is created. The product table we could have created it first or second or third, would have been totally fine because it stands alone. It has a single primary key, which is the product ID. The order line table is the last table to be created, and it has to be the last table to be created because it requires the foreign key from the order table, and the order table requires the primary key from the customer table, and it requires a foreign key from the product table, so the product table has to exist as well. So it has to be the last table that you create. And I'm trying to stress this because it seems like in some cases the order creation could be arbitrary, but it is often not. If you have a table that has just a primary key and no foreign keys, it can be one of the first tables to be created. If a table has a foreign key, the other side, the primary key, has to have already existed before that table can be created and its constraint can be created. So the order of these commands absolutely matters to get a database set up correctly. And we are going to find that there are a couple of database structures where we have a chicken and the egg scenario, where I can't create one table because it refers to another, and I can't create that table because it refers back to the first one. And so there may be some situations where we create tables that are not properly constrained, and then we go back and retroactively add some constraints. It's this weird situation where the first time we create it, we got to monkey around with it a little bit. And then once we get it in there in the books at least once, then we can go back and create some constraints. And I will definitely talk about those when we get a little bit closer to them. They're interesting for sure. So this is what it looks like to create tables. Again, here's some other examples. We create the product table. There may be some additional defining of attributes and their various data types. So this is really interesting here where you have this check the product finish in the attribute for product finish, and it specifically has to be either cherry, natural ash, white ash, red oak, natural oak, or walnut. So this is a furniture company, obviously, and the product finish has to be one of these wood types. So this is an additional constraint that we're adding for the product finish called a check, where you have to enter one of these different values. So I would kind of think about this as you're filling out a form and you have a little drop down for product finish, and you can only choose one of these 6 types of wood for the product finish. It has to be one of those 6 things, which is kind of cool. This next one also talks about obviously not null, so making sure that we have to have not null for our primary keys. Anything else is allowed to be nullable. Sometimes we have primary keys that are composite. So for that order line table, not only did it have 2 foreign keys, FK1 and FK2, but it also had a primary key, which is the combination of those 2 fields. So the way you create a composite primary key is you type the constraint, you type the name of the constraint, and it's usually the name of the table underscore PK. That's very common notation. You're creating a primary key, and then in parentheses, the various attributes that make up the primary key in combination. What this means, of course, stress this many times in this class, is that order ID by itself is not unique. Product ID by itself is not unique. What is unique is the combination of those 2 things. So imagine you have to type the entire thing as one big field, and that is unique. So you can't have a product show up in an order ID more than once. Because what you would want, if that was the case, if you're trying to type the same product twice, is instead you'd type that product once and you'd increase the order quantity by some amount. So you'd never want the product to show up more than once in an order. And this rule, this primary key where the 2 things being combined are unique, is actually enforcing a business rule, which is, hey, you can order as many of a particular product as you want, but it's not going to be separate line items. It's going to be a single line item for how much of that product you can order, and we'll just adjust the quantity accordingly. You can't order the same product in 2 different places. So enforcing a business rule with a database constraint, which is a really important idea. You can see here some controlling of the values and attributes. Again, I already talked about the domain constraint, which is the finish of the wood. But the other one you can see up top here for the order table is the date has a default date, which is whatever the system date is. So whatever the computer is currently reporting, the server or the client is reporting as the date and time. That's the default date and time for that order. Is it possible that you can change it and say, actually, this order was placed a couple days ago and I only just got around to it? Sure. Or it's some sort of future order, so I'm going to date it into the future. Yeah, absolutely. But if you don't type anything, it's going to default to today's date and time, which is a cool idea. I already talked about foreign key, but this slide tries to further emphasize that if you have a primary key in a table, it could exist as a foreign key someplace else. So the foreign key has to be able to reference a different table, or perhaps the same table. Sometimes we have some references to the same place. And you can see here that it's referencing the customer table and it's specifically referencing the customer ID in the customer table. So you can follow along with the syntax fairly straightforwardly to get your foreign keys into your database. Next, we want to think a little bit about data integrity and the various controls that we program into our database to make sure that our data is staying in its proper format. One type of data integrity is referential integrity. This is a constraint that ensures that the foreign key values have to match the primary key values of a related table, There are a couple ways you can restrict how this relationship works. One is you could potentially allow for the deleting of the primary record, and that might affect the foreign key side of things. One might be that when you update the primary key, it automatically updates things that are foreign keys based upon that primary key. That's really neat. Might be that it automatically does insertion of dependent records. So let's talk a little bit about how this might work. Here we've got a situation where we've got customers, and customers are part of the order table, right? An order can't exist unless it was placed by a customer. So what we could add in our database is how we handle on update. You can see these various statements for on update. We could do an on update restrict. We could do an on update cascade. We could set nulls. We could set defaults. So if we do an on update cascade, what that means is if you change the customer ID, all of the orders that are associated with that previous customer ID now get associated with the new customer ID. So I was in the database, I was customer number 2. I get changed in the database to customer number 37. In the order table, everywhere where we saw customer number 2, we would now see the number 37 instead. It cascades the one side into the many side, so kind of flowing down the waterfall from the one side of the relationship to the many side of the relationship. That's on update cascade. On update restrict, that first one, all it's doing is not allowing you to type a foreign key in the order table that doesn't already exist in the customer table. That's kind of the default. If you do on update set null, if you change a customer ID, the customer ID in the order table will get set to some sort of predefined value. So now those orders just kind of default to nobody. So if I get changed from customer 2 to customer 17, all the orders that were associated with customer 2 are no longer associated with that customer, because that customer is not me anymore. They're not associated with 17 either. They're associated with nothing. They're associated with some sort of default value. And that wouldn't be great probably for orders, but for some databases that would end up making sense. So we'd have to think about where we might want to do that rule versus a cascade. Okay, so there are all kinds of interesting ways that we can manipulate the data relationships by using these on update statements. After you have created your database structure, we're going to eventually talk about how we're going to populate the databases and then how we're going to manipulate the data within those databases. And that's a completely different topic. But every once in a while, after a database has been created, you're going to want to go back and change the structure in that database. And so one of the ways you can do that is with an alter table statement. So you could change the structure of a table. This is not something you want to do on a regular basis. I mentioned when we talked about normalization that we tend to want to create tables where their natural movement and dynamic component is only up and down, where we're adding rows or deleting rows as far as adding or deleting information. We're typically not adding or deleting columns. We're going to constrain the movement to just up and down. But if you do need to change something sideways, like adding a column, you would do it with an alter table command. So this is not something that happens normally. This is something that happens as you redesign a database. So you can see you could add a column, you could alter a column, and you could change something about it, like changing its default value. You could remove a column by using the command drop default, so you can get rid of something. You could change its restriction or its cascading. You could add an additional constraint. So there are things that you can do after the fact to get rid of certain pieces of information or add pieces of information or change pieces of information in your table structure. But these will be rare. Again, you might use them if you decide to use your database in a slightly different way. You might use them as part of the creation process if you've got some sort of constraints that kind of banging up against each other. So you might have to do something sort of interesting as far as altering after the fact. But these aren't going to be things we use on the regular basis. So the example there is, you can see they're adding a new column. In this case, it's a column called customer type. It gets a variable character with a length of 2, and its default value is commercial. Other things you might have to do from a mechanical standpoint is every once in a while, we might want to get rid of a table. You want to completely delete a table absolutely from your database. This is something you want to be very careful about, but you can drop a table from the database doing a drop table custom, and the entire table will disappear. That does potentially break all kinds of things. So you may get yelled at that you can't drop a table because it's connected to other tables, and it would break all kinds of constraints. So this may not work in certain scenarios because of the way your database is structured. You may not be allowed to drop certain tables, but sometimes you will, and sometimes you can. Some databases create kind of temporary tables to work with, and then they drop them once they're done with them. That's a way that some databases function. So that is certainly a possibility. Another thing we could do is we could potentially just remove all the information from a table, but keep its structure. So this would be, look, I want to keep the customer table and I want to keep all the various constraints, but everything that's in the customer table, I want to say goodbye to it. So we're going to get rid of all the information that's in that table, and that'd be a truncate statement. And again, sometimes we have tables where we temporarily store some information and get rid of it, and temporarily store some information and get rid of it. A truncate table command might be used in those scenarios. Okay, so that is a quick, dirty conversation on how we're going to create our databases. And we're going to be spending some time here for the next lecture or two creating some databases in SQL Server. That's something I'm going to be demonstrating on Thursday. So again, if you can, I'll put some instructions up here in short order. Get SQL Server installed on your computer between now and Thursday. We'll be going through a demonstration on how we're going to create some databases in SQL Server on Thursday, and you can play along, or you can just watch me do it, and then you can go do it on your own after the fact if you'd like. So that's kind of our roadmap moving forward. Between now and the next couple of weeks, if you want to review your exam with me, please schedule a meeting with me via Calendly. I'll be happy to meet with you and talk about how your exam went. If it didn't go the way you wanted to, I'll also be talking to you about what we can do to adjust your study habits and all that sort of thing. I'm happy to do that as well. All right. Thank you, everyone, for your contributions today, and I will see you all on Thursday.